Welcome to Digital VLSI Design Virtual Lab, experiment number 7, registers. The aim of this experiment is to design and plot the characteristics of a master-slave positive and negative edge-triggered register based on multiplexer. In order to proceed to the experiment, click on the Simulator tab. Here two separate links are provided, one for the dynamic characteristics of a rising edge-triggered register and the other for a falling edge-triggered register using ngSpice. Now we will see the dynamic characteristics of a rising edge triggered register using ngSpice. Click on link number 1. A new page will appear where on the top left you have the block diagram of the rising edge triggered register and on the right side the spice code. Now we will see how the register is implemented. Looking at the spice code, first we have a sub-circuit implementation of an inverter, which we have already seen in the previous experiments. It is then followed by sub-circuit implementation of active high latch with a sub-circuit name H latch, followed by an active low latch in the name L latch. Then we have three voltage sources VC, which is connected between node N1 and ground, which acts as the static power source with a DC voltage of 1.8 volts. Then we have Vin, which is the data input, which is connected between node N2 and ground. Then we have the clock, which is connected between node N3 and 0. The various parameters of these sources are defined such that the frequency of clock is high compared to that of the input signal. The figure shows how the voltage sources and two modules Xn and Xp, which represents active low latch and active high latch respectively, are connected to form the rising edge triggered register. Then level 49 model for PMOS and NMOS are defined, and we end the program. And finally we have a transient analysis command which runs the simulation for 30 nanoseconds with a sampling rate of 1 nanosecond. Now click on the Simulate tab to see the waveforms. ngSpice will generate three separate waveforms, one for data input, the other for clock, and finally the output. It can be verified that the output changes only at the rising edge of the clock. Now we will find the setup time of the register. We know setup time is a minimum time that the input should be stable before the active edge of the clock. For that, first we will select one time slot where the input changes. Let's take the change of the input from low to high at this 10 nanosecond as our point of interest. Now we will select an active edge, say the edge at this 9 nanosecond, and we will move the clock towards right so that this edge coincides with this input change. For that, we will introduce a delay of 1 nanosecond to the clock signal. Then click on the Simulate tab. We can see now the active edge coincides with the input change and there is no corresponding change in the output. That means the setup time is not satisfied. So now we will give an additional delay of 50 picoseconds so that active edge comes 50 picoseconds after the change in input has occurred. We also change the transient analysis time from 5 nanoseconds to 50 nanoseconds to get a better view of the waveforms. From the output we can see that 50 picoseconds is not sufficient for setup time. So now we will try with 100 picoseconds. Now the output has changed, which indicates that setup time is less than 100 picoseconds. So setup time is between 50 picoseconds and 100 picoseconds. So now we will try with 70 picoseconds. We can see that 70 picoseconds is sufficient to meet the setup time. So we will try with 60 picoseconds. the output has not changed, which indicates that 60 picoseconds is not sufficient to meet the setup time requirement. So we got 70 picoseconds as our setup time. In this way, we can proceed to find the hold time also, and we can see that hold time is 0 in this case. Now one can go back to the simulator tab and click on the second link to perform the experiment on falling edge triggered register. Thank you.